Hello all, and for those of you who are new, welcome to this channel and this video. Today we're gonna do something for the first time, which is to go over a past paper from the GCSE level, okay? And again, I will start with the international exam, okay? So this is paper 1P, and I noticed that there is also a paper 1PR, which is taken in certain areas of the world. I might go over those papers too. So this is Unit 4 PH1, and I believe it's taken by Year 11 students who follow the international curriculum of Edexcel, okay? So we will see how this goes. If people find these videos useful, I might upload more. If not, I might continue with what I have been doing, which is mostly A-level physics units 1 to 6. And recently, I also started working with paper 1 and 2, and hopefully, I will do more from the UK Edexcel curriculum. So I will probably stay within the Pearson Edexcel universe for now, and go over papers and see how this goes. So let's start. Oh, before we start, notice that this is something I always tell my students. There's a time limit of 2 hours in this exam, right? And there are 110 marks from what I saw. So a rule of thumb is that, for example, if we go to the first question, we see that it awards 7 marks, right? So this question should take you about 7 minutes. So that's the rule of thumb. So 1 minute per mark, okay? If it takes you 10 minutes, maybe the next question will take you 5 minutes and you will earn that time. So don't freak out. I mean, it's not a hard rule or something, but it's good to time yourself when you take these tests. Okay, they give you some formula in the beginning, and there is also, I'm sorry for being thorough about this, but this is the first time I'm uploading a video like this. I mean, from the year 11 curriculum, okay? Okay, and you have many formulas in the back related to the test. So yeah, what else? Okay, let's start with question 1. Let me find it. So, okay. Okay, some questions must be answered with a cross in a box. If you change your mind about an answer, put a line through the box and then mark your new answer with a cross. Okay, those are the instructions. So, question 1. This question is about stars. Question A, the table gives information about 4 different stars. Betelgeuse, very famous star. Don't know why people are so obsessed with it. It's because I guess it's expected that it's going to go supernova and explode. Maybe even within our lifetime. I don't know. Nobody knows actually. So we'll see. It's going to be amazing if it explodes because I think it's going to be visible for a long time. So, question I, which of these stars has the lowest surface temperature? And this is incidentally Betelgeuse. Why? Because you're going to learn about this at the A level. Okay, this is the price you will have to pay if you follow along with me. I like going into detail. I taught A-level physics. I taught undergraduate level physics and even graduate level physics. So the way to find this is to work with the HR diagram, the Hertzsprung-Russell diagram. The temperature is in the bottom and it increases to the left. Okay, so if this is 5,000 Kelvin, this is 20,000. Okay, and the luminosity is in the vertical axis. Okay, and it looks something like this. And Betelgeuse as a supergiant will be all the way up here. Okay, it will have a low temperature, whereas Sirius B as a white dwarf will be somewhere there. Sirius A is a main sequence star. It will be, I don't know, somewhere there maybe. And the sun, it will be further down, okay, because it has less mass. So, which of these stars has the lowest surface temperature? Is going to be Betelgeuse. And the reason is because it's a red supergiant. Okay, so let's move on. Question 2: which of these stars will become a supernova in the future? And again, it's the Betelgeuse, because this is the life cycle of stars. Okay, they start as nebulae, and then they become main sequence stars, so they are somewhere here. Then they become supergiants or giants. Okay, and then the supergiants explode and become neutron stars or black holes, whereas giant stars just become white dwarfs, so they move all the way down there. Okay, anyway, I hope this is not confusing. If it is, let me know in the comments, and I will be more thorough in future videos. So question 3: Sirius B and the Sun have approximately the same mass, but are different colors and in different evolutionary stages. Describe two other differences between Sirius B and the Sun. So, as I said earlier, I erased the diagram, but since they are both main sequence, right? But Sirius A is heavier, it has more material to burn, so it's hotter. So, okay, Sirius B, Sirius is with an I, sorry. Sirius B is hotter than the Sun. Okay. What else can we say? Let me see. Wait. I got myself confused. Let's erase all this. Okay, I made a mistake, guys. Okay, sorry. It's the first time I'm doing this, so okay, I'm sorry. So again, let's start over. So we're comparing the Sun. Okay, this is the Sun and Sirius B. Okay, Sirius B is a white dwarf. Okay, so what I said actually was correct. Sirius A is indeed hotter than the Sun, but let's focus on Sirius B. Sirius B is still hotter than the Sun because it's a white dwarf. Okay, so Sirius B is hotter than the Sun. Okay, it's also denser, right, and smaller. So Sirius B is smaller, thus denser than the Sun. Okay, they ask for two differences, right? And we provided two, but you can also say, I mean, just to complete this, Sirius B contains less hydrogen. How do we know this? Because it's a white dwarf. It burned through its hydrogen. Okay. I'm also sipping my coffee. So, question B: Sirius B orbits with Sirius A as part of a binary star system. The mean orbital radius of Sirius B is 29.7 times 10 to the 9 kilometers. The time for Sirius B to complete one orbit is 50 years. Calculate the mean orbital speed of Sirius B. Give your answers in kilometers per second. Okay, so I mean, I know the formula, but I want to see where it is in the paper. It's over here. So orbital speed. This is what we need. Okay. And at the A level, you will figure out, I guess, where that formula comes from, because I think at this level, year 11, you just use formulas, you don't really derive them. And guys, physics is way more fun when you derive things from first principles. So let's do this. So V is 2 pi r over the period. I don't know. Write in the comments, but I believe in year 11, I never taught students as young as year 11. Okay, I only taught down to year 12. That's my threshold, I guess. Okay, I mean, I really like teaching older students and undergrads and graduate students. But I'm sure it might be fun. So I think you write the multiplication with a cross still at this level. So I guess what I wrote on the left is equivalent to 2 pi r over tau. So, okay. So this is 2 pi times 29.7 times 10 to the 9, and it's in kilometers, so we will leave it like that. By the way I solve problems, I put all the numbers to the left and all the units to the right. So the units for what we have in the top expression is kilometers, okay? And in the denominator we have 50 years, and 1 year has 365 days. 1 day has 24 hours. 1 hour has 60 minutes, and 1 minute has 60 seconds. And I put my seconds down there to the right, okay? And if we perform the calculation, we will find 118.35 kilometers per second, which you can write as 118 kilometers per second. And this was question 1. Okay, let's move on to question number 2. Okay, I have my notes here. So, a car travels at a constant speed of 14 meters per second along a road. Calculate the distance traveled by the car in a time of 30 seconds. Use the formula distance traveled is average speed times time taken. So, okay, let's write this down. Distance traveled is, again, you see they use a cross, okay, at the A level. So when you become year 12, for those of you who will continue to take physics, please do. Physics is fun, okay? You use a dot to represent a multiplication or nothing at all, okay? But anyway, so it travels with 14. Again, the units are meters per second. And then 30 seconds, 30, and I put my units down here. Seconds is on the numerator. Seconds cancel. So 420 meters. Question B. The driver of the car sees an obstacle in the road ahead and applies the brakes. Which of these is a description of the thinking distance of the car? What's the thinking distance? I admit that when I was solving this, by the way I work through past papers is that I solve them myself, okay? So because I want to have an opinion of what's going on. I don't look at the mark scheme unless I need to, or just to compare my solutions with their solutions. So when I saw this, I didn't really know what the thinking distance is, but I guessed it. I mean, it's the time taken for the driver to notice the obstacle and apply the brakes. So this is option B, distance travel between seeing the obstacle and applying the brakes. Okay. Which of these factors would increase the braking distance of the car? So car traveling at a lower initial speed, that will decrease it, right? B, driver being tired. I mean, okay. C, worn tires of the car. That's the answer. Why? Because less friction. Okay. And 3, state the only factor that affects both the thinking distance and the braking distance of the car. And this is speed, right? Speed as the car will travel further while thinking and braking. So it affects both. All right. Question 3. Okay, question 3. This is a simplified diagram of the electrical wiring in a house, and they show circuit breakers at 6 amps for lights and 32 amps for sockets. Question A. A current larger than 32 amps flows in the sockets Describe how having the circuit breaker in series with the sockets protects the house. So if the current, and for those of you who are watching these videos for the first, this video, I'm sorry, for the first time, I have to warn you that my handwriting is not the best you have ever seen, but I'm doing my best. Okay, so if the current becomes larger than 32 amps, okay, the circuit breaker trips, and this breaks the circuit. Okay, and stops the current. Stops the current, preventing overheating. And there's a circuit board in everybody's house, and you will see these breakers, I guess. So I have to warn you that I studied theoretical physics, which means that I'm not the best person in the world when it comes to equipment and experiments and stuff like that. So question B. A student suggests that fuses could be used instead of the circuit breakers. Give the two disadvantages of using fuses instead of circuit breakers. So when a fuse melts, melts, you need to replace it. Okay, you need to replace it. Whereas you can simply reset the breaker. Okay, and two, there's a slower response. Okay, slower response. Circuit breakers use thermal mechanisms, I'm sorry, and trip quickly. Again, I warned you about my handwriting. And trip quickly, whereas fuses need to melt, which takes longer. All right, and C, explain why the wiring in the house includes an earth wire. So when fault occurs, okay, current flows through the earth wire. Okay, that's it. And this trips the, okay, this, you can also write this trips the circuit breaker. All right, let's move on. Question 4. The diagram shows a force pulling a block up a ramp. Okay, show that the work done by the force is about 440 joules. Okay, use the formula work done is force times distance. So let's do that. So it moves by the way, for the work done, okay, you use force times, how do they call distance at the GCSE level? I think it's D. Okay, so the force and the distance have to be in the same direction. So you see here that the force is in the direction of the incline, and so is the distance. So these are the two distances, sorry, quantities you have to multiply. Okay, don't get confused with the vertical. Okay, right. Okay, so work is 120 newtons. Oops, I said that I will put my units to the right. So 120 newtons times 3.7 meters. Newtons times meters makes a joule. So that's 444 joules, which is about 440 joules. B, the block gains 12 joules of energy in its gravitational store when it is lifted through a height of 0.82 meters. Calculate the mass of the block. Okay, so this is just the gravitational potential energy formula. Okay, so mgh is 12, so the mass is 12 joules over 9.81, that's meters per second squared, and h is 0.82 meters, so we have meters squared there. Okay, so the result is 1.49, and then we have joules. Let me use a clean page to explain this. I don't know if they explain it to you at the level of physics you are taking, but okay, we have joules over meters times second squared, right? Yes. So 1 joule, one joule is 1 kilogram times meters squared over second squared. So if we combine this, we see that we have kilograms meter squared over second squared times second squared over meter squared. So everything cancels to give you kilograms, okay? So that's kilograms, and we can write this as 1.5 kilograms. Moving on. C, a student states that most of the input energy is destroyed when the block is pulled up the ramp. Comment on the student's statement. It's not destroyed, it's lost. Okay, that's different. So energy, so the first statement here, the first statement we can make against the student's argument is that energy cannot be destroyed. Okay. And again, recall that energy can only be transferred to something else. Okay. So where is this energy transferred then? I mean, if it's not destroyed, where does it go? It becomes heat, right? So here energy is transferred to heat, and probably the heat is due to friction of the box with the ramp. Okay, this was question number 4. Moving on to question number 5. Probably my most favorite in the test, because if you read my channel's description, I have a PhD in nuclear physics and I really love these things. So let's move on. This question is about radioactivity. Uranium-238 decays by emitting an alpha particle to become an isotope of thorium. Complete the equation of the alpha decay of uranium-238. Okay. I don't know how they call it at the GCSE level, but this is the mass number of a nucleus, and this is the atomic number or proton number. Okay. And I guess you need to know by heart that the mass number of the alpha particle is 4 and the number of protons is 2. This is the helium-4 nucleus. Okay, so if we have 90 plus 2, we need uranium to have 92 protons. And then since the mass number is also conserved, we need thorium to have 234 protons and neutrons. Okay. Question B, The isotope of thorium produced in the decay of uranium-238 is also radioactive. Thorium decays by emitting a beta particle. Describe how the structure of a thorium nucleus changes when a beta particle is emitted. Okay, so the story is that the beta particle is negatively charged. Okay, how does this happen? A neutron decays into a proton and a beta particle and an electron and a neutron. You will learn about that at the A level, or maybe you already learn about this at this level. Okay, so the number of neutrons will decrease by 1 and the number of protons will increase by 1. Okay, so the number of neutrons will decrease, okay, decrease by 1, and the number of protons will increase by 1. And for the first time I noticed that it says do not write in this area. Okay, so yeah, in the future, okay, maybe I can move this, okay, there, so it's not in the area, even though I'm not being tested, guys. But anyway, as a bonus extra, you don't need to know this, but the actual reaction is you start with thorium-234 and 90 protons, and this decays to something called palladium-234 91 plus a beta particle which has a charge of -1 and 0 mass number plus an electron and a neutrino. And the underlying reaction is that a neutron decays into a proton plus an electron plus that. Okay, you will learn about this in your future life, so your future self will know about this. So question C, a teacher demonstrates radioactivity using a radioactive rock. So that doesn't sound good, but anyway, okay, the rock contains uranium-238 and other radioactive isotopes. The teacher takes precautions to reduce the risk of contamination and irradiation by the radioactive rock. I suggest a safety precaution that will reduce the risk of contamination by the radioactive rock. Wear gloves, okay? Wear gloves, please. Okay, don't write this in the exam, okay? Also, don't drop the rock. Okay, why? It might break, the fragments might go everywhere. There might be dust that goes into your respiratory system. Not a good idea, okay? So, let's move on. Part 2. Suggest a safety precaution that will reduce the risk of irradiation by the radioactive rock. Okay. Minimize exposure time. Okay, minimize exposure time. What else can we say? Keep it at a distance. Okay, keep at a distance. All right. And now part 3. The teacher measures the amount of radiation emitted by the radioactive rock in a time of 1 minute using a Geiger-Müller tube and counter. The teacher repeats this measurement to obtain a total of 5 measurements of the count rate. The table shows the teacher's results. Okay, calculate the mean count rate. Give your answer to 2 significant figures. Okay, first of all, we have an outlier here, okay? So that's an observation you have to make. So eliminate that from your mean and take the other ones and find the mean. So 54 plus 58 plus 52 plus 55. We have 4 measurements, right? So we have to divide by 4 to find the mean. And the mean is 54.75 counts per minute, sorry. Okay, and okay, this is about 55, I guess, counts per minute. All right, moving on. Question 6. This question is about magnetism, and we all like magnetism. Okay, diagram 1 shows the ends of two strong bar magnets and the space between the bar magnets. Okay, there is a uniform magnetic field in the space between the bar magnets. One of the magnetic field lines has already been drawn. Complete diagram 1 by drawing three more magnetic field lines and labeling the poles of the bar magnets. Okay, first of all, the field goes from the north pole to the south pole because the arrow points to the right, as you see the page. And now we have to draw the three more lines at least. Okay, they have to be equally spaced. So that's the first one. That's the second one. Okay, and that's the third one. Okay, and the arrow points to the right. Okay, simple as that. And this spacing has to be approximately the same because it's a uniform field. Okay, let me erase that. Okay, let's move on. Part 2. Describe a method a student could use to show the shape and direction of the magnetic field between the bar magnets. You may draw a diagram to help your answer. Okay, you can use, okay, I'm going to write down here and maybe I will draw a diagram. So use a compass. Use a compass that you move around in different locations. Okay, or many compasses if you have them. Okay, you can also use iron fillings. Okay, and the idea is that this is the north pole, this is the south, so you can put compasses that will point something like this, right? Okay, and then you can connect the dots. Okay, I mean, if you have three compasses pointing in the same direction like that, you connect them and you draw an arrow. Okay, so something like that. Name a magnetically soft material. Okay, that would be iron, cobalt, my favorite. I can't think of anything else. So let's move on to part B. A student investigates how the length L of a current carrying wire in a magnetic field affects the size of the force on the wire. The student uses a power supply and keeps the current in the wire constant. So the current in the wire is constant. That's a key there, okay? They use the same magnet through the experiment. Okay, so that's another key. Diagram 2 shows part of the student's equipment. Okay. Table 1 lists the variables in the student's investigation. Add one tick to show to each row to show whether each variable is an independent, dependent, or control variable. Okay, so the current is a control variable. Why? They say tick. Okay, so let's put a tick. It's a control variable because it's constant. Okay. The length of wire in the field is an independent quantity because you can change it. Okay. Independent variables are those that change by themselves. Okay. The force on the wire is the dependent variable because this is what we are studying. We are studying how the force changes due to changes in the independent variables. Okay, so that's a dependent variable. And then the magnetic field strength is kept constant, so that's a control variable. Okay, let's move on. Table 2 shows the students' results, length of wire and field in millimeters and force in newtons. Plot a graph of the results on the grid. Okay, this is something I will have to do now because I haven't done it. I was lazy when I was solving the paper, so let's do it. So we have vertical axis for the force, okay, and horizontal for the length. Okay, so the length is in millimeters, and the force is in newtons. Okay, so the length goes in nice increments of 5. Okay, do we have enough squares? We have 1, 2, 3, 4, 5, 6, 7 measurements. So here we have 1, 2, 3, 4, 5, 6. Not enough, but maybe we can make it enough by pulling this. Let's pull this. Can we? Yes, we can. Let's pull it there. Okay, now we have enough space. And I'm gonna move this as well. Okay, up there. And that doesn't bother us. Okay, let's move on. So let's put 0 there. Okay, and we have 5, 10, 15, 20, 25, and 30. I guess we didn't have to do that, but anyway. And then the force goes from 0 to 2. We can make it, we can use the boxes in increments of 1 is not enough, 0.5. So 0.5, 1, 1.5, and 2. At some point, I will speed up the video, but let me do 1 point. So for a 0 length, we have 0 force. Okay, I'm going to use green and put that point there. For 5 millimeters, we have a force of 0.32. Okay, so that's over there. Okay, why? Because this is 0.25. Every small square is 0.25 over 5. So 0.05 is each. So this little square, I mean, is an increment of 0.05. Okay, because this is 0.25. So yeah, that's the reason. And now I will speed the video for you. Okay. All right, I'm back. You see that the graph is now complete. And then 3 asks to draw a line of best fit. Okay, so let's do that. I guess this is a line of best fit. Okay, something like that. So line of best fit, you have to have as many points on this side as you have on this side, and your line has to pass through as many points as possible. You don't have to force it to pass from 0, but okay, we did this here, but you don't have to. Okay. And let's do part 4. The student repeats the experiment, but with a smaller current in the wire. Draw another line on the grid to show the expected results when using a smaller current. Okay, to answer this, I need to make sure that you guys know the formula that connects the force that the wire experiences with the magnetic field, the length, and the current, because that will make it easier for me to explain it to you. So let's look at these formulas over here. Do they mention anything? They don't. So let's go to the back and see what they give us about magnetism. I'm curious. All right. Forces, electricity, waves, energy, resources, solids, and astrophysics. So sadly, you don't learn about this. So, okay, I'm going to explain it differently. Okay, so if we look at the graph, okay, the graph tells us that the force increases with length. So the force is actually proportional to the current that passes through the wire. So if we have the gradient of this curve is proportional to the current. So with a smaller current, we will have a line with less gradient. Okay, it's gonna be less steep. Okay, so less current. And we can explain it down here. So force is proportional to current. So a lower current will produce a line that is less steep than before. And we can write in parentheses that the gradient is proportional to current. Moving on to question 7. The diagram shows an electric circuit used to determine the brightness of the light in a room. Add the voltmeter to the diagram to measure the voltage of resistor R. So it needs to be in parallel with the resistor. That's that. Okay. Okay, let me fix this line there. Okay. B, state the formula linking voltage, current, and resistance. This is Ohm's law. V over I. I don't know why they ask you this. Let me see. Is it in the back of the paper? Do you have to memorize? Yeah, it's there. So I don't know why they ask you this question, but I guess I don't know. They want to make sure you know them. You can also write it as V equals I times resistance. Okay. 2. The voltage across resistor R is 1.9 volts. The resistance of resistor R is 800 ohms. Calculate the current in the circuit. Give your answers in milliamps. So I is V over R. So that's 1.9 over 800. So 2.38 times 10 to the negative 3 amps, which is 2.38 milliamps, which we can also write as 2.4 milliamps. Okay. C, explain why the voltage across the light dependent resistor decreases if the brightness of the light in the room increases. So the resistance of LDR, okay, decreases as brightness increases. And the reason is because you have more charge carriers in your LDR, so there is less resistance because the current can easily pass. So current increases, okay. The voltage across the fixed resistor increases, right? Because more current passes through it. Now, since the battery is the same, okay, the battery is the same, and since the voltage of the battery is equal to the voltage of the LDR plus the voltage of the resistor, then if VR increases, VLDR decreases so that V is constant. Okay. Did we explain the right thing? Okay, let's read again. Explain why the voltage across the light-dependent resistor decreases if the brightness of the light in the room increases. Okay. Question D. Another resistor is connected in parallel with resistor R. The new resistor has a higher resistance than resistor R. Explain what happens to the current in the LDR. In the circuit diagram, assume that the brightness of the light in the room remains constant. So, I don't know if you learned this at this level, but when you connect, in this case we have R, and they say that we connect another resistor R prime in parallel. Okay, actually, to make it simple, let's draw it like this. Let me know in the comments if you learn about this. Actually, let me check the back of the paper and see if they have relevant formulas. Do they? No. Okay, so you will learn about this at the A level, but I'm going to explain it anyhow because this is what I do. It's in my nature. So you can replace this with a total resistance. Okay, so you can think about this as R total. Okay, and then 1 over R total. So I'm trying to say this combination in the bottom is equivalent to the top, with 1 over R total equal to 1 over R plus 1 over R prime. Okay, so the total resistance, and we can find the common denominator. So this is R prime plus R over R times R prime. So R total is, let me see, R times R prime over R prime plus R. Okay, so this is going to be lower than the resistance R itself. Okay, so let's write this down. So R total is smaller than R. Okay, you can see this by, how can you see it? Let's say that this is 10 ohms and this is 20 ohms. Okay, so our total is going to be 10 times 2200 over 30. Okay, so 20 over 3 is, what is it? It's something that is less than. So 20 over 3 is 6.7 ohms. Okay, so this is 6.7 ohms, which is less than 10 ohms that we started with, right? So our total is less than R. So let's go back and answer that the parallel combination, okay, we have R total lesser than R. So the current in the LDR increases, okay? And also there are more paths for the current in the circuit. Okay. All right, let's move on to question 8. The diagram shows a pot made of clay. Describe a method that could be used to accurately determine the volume of clay used in the pot. So you can use the displacement method. By submerging the pot in water. Okay, collect the displaced water and measure its volume. Using a measuring cylinder. Okay, measuring cylinder. Okay, repeat the measurement and calculate the mean. Repeat the measurement and calculate mean, and ensure pot is fully submerged. Is fully not measured, submerged. I'm sorry, submerged, and you measure volume at eye level. Okay, Give the name of a piece of apparatus that could be used to measure the mass of the clay pod. You can use a top pan balance. Top pan balance. All right. C. The clay pot can be used to hold liquids. A student needs to determine the volume of liquid that can be contained in the pod. The student measures the mass of the empty pod and then measures the mass of the pod again when it is filled with a liquid. The table shows the student's measurements: mass of empty pod in kilograms, mass of pod filled with liquid in kilograms. The density of the liquid used is 920 kilograms per cubic meter. Calculate the volume of liquid that can be contained in the pod. Use the formula density is mass over volume. So the mass is of the liquid is 6.8 minus 1.2, so 5.6 kilograms. This is an equal sign. Okay, and then rho is m over v, so v is m over rho, so that's 5.6 over 920, so the volume is 0.0061 cubic meters. If you calculate this on your calculator, it will show 5.6. Let me do it quickly. Your calculator shows 6.1 times 10 to the negative 3. Okay, this means this is equivalent to 3 zeros, right? This is what it tells us. So 1, 2, 3, and then we put the dot there, and then 61. Okay, so this is what it means. So this is equivalent to 61 over 1000, pretty much. So the 6, I'm trying to say that when you see an expression 6.1 times 10 to the negative 3, okay, so this is equivalent to that. If it was 6.7 times 10 to the negative 4, you need 4 zeros. So 1, 2, 3, 4, and then 67, and you put the dot there. Okay, this is correct. Yes. And yeah, I mean, in case you don't know. Right, question 8 is done. Let's move on to question 9. That's a really cool car. What is it? Please write in the comments. It looks American, or is it not? I don't know. Write in the comments the model of the car. So the photograph shows a cool car. Okay, being driven along a straight racetrack. The car starts from rest and accelerates along the straight racetrack. After crossing the finish line, the driver applies the brakes to bring the car to rest. The graph shows how the velocity of the car changes with time after the car starts to accelerate. Okay, what feature of the graph gives the magnitude of the acceleration of the car? So since you're given velocity with respect to time, it's the gradient of the line. Okay. The area between line time and time axis is v times t, pretty much, which is distance. Okay, how do I know that? Because velocity is given in meters per second, and then if I multiply with seconds, I am left with meters, so that's a distance. Okay. Anyway, let's move on. Part B. At which point on the graph does the driver of the car first apply the brakes? That will be point Q, right? And the reason is that it stops accelerating and it starts decelerating. So that's option B. Explain why the graph is a curve for the first 11 seconds. So let me erase this and show you something. I don't know if they teach you this. Let me know in the comments, guys, what they actually teach you at this level, because I never taught year 11. Or year 10. I only taught down to year 12 and year 13. Okay, if I teach again in an official school or classroom, That's the minimum I will go probably. Okay, I mean, I like more challenging material. So anyway, I shouldn't say that, should I? Anyway, uh, maybe I will give it a shot in the future. But anyway, for the moment, I'm making videos, so I like it. So let's move on. So to find the acceleration, you need to find the gradient of the line, and for a curve, the gradient is the tangent to the line. Okay, so that's the initial acceleration, and this is how it progresses. So you see that the tangent becomes less and less steep. Okay, so this is the initial gradient, and this is the gradient after a few seconds, and this is the next gradient. Okay, so you see that the gradient decreases as you go from 0 to q. Okay, so that's the first observation. So the acceleration decreases. Okay, so also air resistance increases, air resistance, which is proportional to V, decreases. Oops. Okay, and the resultant force decreases. Oops. Wait, is that true? So the air resistance increases, so the resultant decreases. Yeah. All right, calculate the distance traveled by the car from 11 seconds to 15 seconds. Okay, you have to go to the graph. Let me use green. So 11 seconds is, okay, so every little square there is 0.25, right? So this is 11.25. So I guess this is, let me see. Okay, this is 11.25. So yeah, it's, okay. Oops. That's the line. Okay. I don't have a steady hand, as you can see. So that's 11 seconds to 15 seconds. So you have to find the area of this triangle. So we have area under curve is equal to the distance, and it's equal to 1/2 times the base, which is 4 seconds, times the height, which is 90 meters per second. So the answer is 180 meters. Okay. This is a long test, by the way, too many questions. So question 10. This question is about light. Light is an example of a wave. State what is meant by the term wave. So waves transfer energy. Waves transfer energy, okay, by vibrations. By vibrations, no matter is transferred. Okay, B. Diagram 1 shows a ray of light incident on a mirror. Draw another ray of light on diagram 1 to show the path of the ray after it is incident on the mirror. Okay, so if this angle is theta, then our outgoing ray, oops, has to, let's start from there. Okay, is this theta? Yeah, I mean, okay. It's reflected by the same angle theta, pretty much, because it's a mirror. Okay. Now, C, diagram 2 shows a ray of red light entering a semicircular glass block from the air. When the ray of red light is incident on the glass air boundary, the light refracts with an angle of refraction of 90 degrees. Using diagram 2, determine the critical angle of red light at the glass air boundary. So we have to measure the angle. I guess, I mean, this is my guess. Okay, so do I have a tool here? So you need to use your protractor, I'm trying to say. So no, they don't have. Yeah, the ruler. Okay. So how do you use this to measure angles? Let me see. Okay, that's 90. Okay, if I line it up, it says 131. We can subtract this from. We can subtract that angle from 180, so 49. Okay, using this silly ruler that the iPad has. So that angle is 49, but you have to use your protractor. Okay, so 49 degrees. So we found our angle by measuring it. Okay, so sine of 49 is 1 over the index we are looking to. Wait, I'm sorry. So using diagram 2, determine the critical angle, so 49. Okay, calculate the refractive index of glass. Sine of 49 is 1 over the index of refraction, so n is 1.3. 1.3. Okay, and 3, the refractive index of blue light in glass is higher than the refractive index of red light in glass. A ray of blue light has an angle of incidence equal to the critical angle of the red light. Okay, explain what will happen to the ray of blue light at the glass air boundary. So higher n means lower critical angle. Okay, since angle of incidence is greater than theta critical, blue light will undergo a total internal reflection. Oops. Okay. Okay, question 11. This was a conceptual question. The diagram shows apparatus that can be used to demonstrate convection currents. I'm sorry. Okay, we have a tube A with smoke and a tube B and a candle. The apparatus consists of a box with 2 tubes A and B that allow air to enter and leave the box. During the demonstration, a candle is placed inside the box directly underneath tube B. A source of smoke is placed above tube A. Using ideas about convection, explain why the smoke moves down into the box through tube A. You may add to the diagram to help your answer. So, okay, the candle hits air under tube B, under tube B. The heated air expands. Okay, its density decreases. Okay, hot air rises and leaves through tube B. Cooler air is drawn in the box through tube A to fill the air escaping. Okay, this sets up a convection current. So smoke is pulled through tube A. So I don't know what kind of diagram they need, but I guess the smoke will go this way. Okay, you will have a convection current. Excuse me. Okay, question 12 is the last question in the test. So this question is about gas pressure. Diagram 1 shows some gas particles contained in a box. The gas particles move in random motion. State what is meant by the term random motion. So particles move in unpredictable directions with unpredictable speeds. Okay, 2. The gas exerts a pressure due to the gas particles colliding with the walls of the box. Explain how these collisions produce pressure. So a force is produced when particles collide with the wall. Okay, so pressure is force per area, so pressure is produced due to this force from the particles. Okay, hope this makes sense. By the way, guys, whenever I say something that doesn't make sense, ask in the comments. I always reply to comments. Okay, part 3. The volume of the box is increased, but the temperature of the gas remains constant. Explain how increasing the volume of the box affects the pressure of the gas in the box. Assume the amount of gas remains constant. So the speed of particles is the same as before. Is the same because T is constant. Okay, that's the first key. And again, I wrote in this space that I'm not supposed to write. So let's move this. Okay, good. Okay, so particles travel a greater distance because the volume is increased. So they collide. Collisions are less frequent. Okay. Therefore, pressure decreases. Okay. So pressure decreases, and I guess that's a good enough answer. So moving on to part B. Diagram 2 shows a device used to measure differences in gas pressure. This device is called a manometer. The difference between the pressure of the atmosphere and the pressure of the gas supply causes a difference in the height of the liquid levels on each side of the manometer. And you see the device. Question I. The liquid in the manometer is oil, which has density of 820 kilograms per cubic meter. The gas pressure difference between the atmosphere and the gas supply is 1850 pascals. calculate the height difference between the liquid levels in the manometer. Use the formula pressure difference is height times density times gravitational field strength. Okay, so we can write that 1850, and I'm not going to use units now, is equal, which is the pressure difference, right? Is equal to the height that we need to find. Let's call it height times 820 times what is the other? Gravitational field strength 9.81. So height is 1850 over 820 times 9.81 in the denominator, and this is 0.23 meters. And I'm gonna take this expression and do a bonus like I did a couple of times in this video. So we have 1850, and that's pascals, over 820, and that's kilograms per cubic meter, and then we have times 9.81, and that's meters per second squared. Okay, let's analyze this. This is a bonus, you don't need to know it. So a pascal is 1 pascal is 1 Newton over square meter. So we have newtons per square meter, then times meters cubed times second squared over meters. And we also have the kilograms from before. Okay, so we see that we have meters times meter squared, meters cubed cancels with this one. And then 1 Newton is 1 kilogram times meters over second squared. So we have kilograms meters over second squared times second squared over kilograms. Seconds cancel, kilograms cancel, and this is meters, which is what we found. Okay, there's no magic in physics. Everything has an explanation. Almost everything. I mean, you have things like string theory, dark matter, dark energy. Those are mysteries. But yeah, many things we can explain. And part 2, different liquids can be used in the manometer. Liquid mercury has a density of 14,000 kilograms per cubic meter. I think it's the denser liquid in nature. And it's a metal. So suggest why liquid mercury could be more appropriate to use in the manometer when measuring very large pressure differences. So mercury is denser. Mercury is denser than oil. Okay, so H is smaller for the same pressure, difference actually. Okay, pressure difference. So larger pressure differences can be measured. And we can see this from this formula that height, we can write it as H is equal to the pressure difference delta P over the density times G. G is constant, so if rho increases, H decreases, so we can measure larger pressure differences. Okay. And now part C, the pressure of a sample of gas is 232 kilopascals at a temperature of 16 degrees Celsius. Calculate the temperature when the pressure of the sample of gas increases to 249 kilopascals. Give your answer in degrees Celsius. Assume that the volume and the mass of the gas sample remain constant. Okay, that's the key. Let's look at the formulas they give us. Pressure over temperature is constant, so this is what we have to use. Okay, And we use this whenever the volume is constant, okay? The other one over there, you use it when temperature is constant, okay? I mean this one. So let's use this one. Let's go back. So first of all, let's calculate T1. Whenever you work with thermodynamics, you always convert Celsius to Kelvin, and then, okay, we will convert back to Celsius. So T1 is 16 degrees Celsius plus 273 gives 289 kelvins. So P1 over T1 is equal to P2 over T2. So T2 is P2 times T1 over P1. I'm going to come down here. So P2, it's, let me see, 249, and that's kilopascals, times T1, 289. That's kelvins. And then in the denominator, we have 232 kilopascals. So kilopascals cancel, and we find 310.18 Kelvin. And if we subtract, I'm sorry, so T2 is 310.18 minus 273. This yields 37.18 degrees Celsius, which is about 37.2 degrees Celsius. And this was my first attempt on paper 1, okay, from the GCSE 9-1 paper from November 2025. This is the international test, okay. For me, it makes no difference to also teach and solve past papers from England. So, I mean, it's the same material. If you guys find this useful, let me know in the comments, and maybe I will produce more of this in the future. But okay, currently I'm focusing on AS and A-level physics, so year 12 and year 13. I plan to make more videos from unit 1 to 6 of the international curriculum, and gradually I want to introduce solutions for paper 1 to 3 and AS paper 1 and paper 2 from England. Currently only for the Edexcel spec. In the future, I don't know, if this channel grows to 1 million followers, subscribers, whatever, I will have time and money to invest and solve other specs. But for now, I'm going to focus on Edexcel and see how this goes. I am also working on other projects that are related to my academic pursuits. So guys, if you like this, please like and subscribe. Let me know what you think in the comments. And if this is useful, I might continue producing this. We'll see. See you in the next one. Bye.